Okay, welcome everyone to yet another session of lecture series session. Today we have Prem Dheeraj with molecular dynamics simulation, third lecture on MD simulations. So this is the lecture was postponed from yesterday because of the festival and the unavailability of two of our group members. So without much delay, I would ask Prem to take over.
Thanks, Arnav. Welcome to another session, guys. So, in this session, we're going to look at basic molecular dynamic simulation in two dimensions. So, whether it is in two dimension or three dimension, the scheme was pretty much similar. But just to put things at a simplified end, I'm preferring to go with 2D, and with very slight modifications, you can actually implement 3D simulations using the techniques that we are going to learn in this session today. So without any further delay, let us just dive into the concepts. So this session would have pretty much everything that we have learned in the previous sessions. And apart from that, few additional concepts will also be disclosed in this particular session. So let's have a quick recap of what we have learned and what we are going to learn in this session. So we started with asking three major questions and answering them, like what is MD, why do we need MD, and how do we do it? After answering these questions, or if, after attempting to answer these questions, we have come to a point where we started looking and exploring basic elements in the algorithm of molecular dynamic simulations. And those basic elements that we have already covered were like velocity overlay scheme, how systems are created or simulation box is created, and what kind of boundary conditions we actually implement in our systems. And to some extent, we have also learned about the potentials. And in this lecture today, we'll have a little overview of what cutoff radius is all about and what minimum image convention is all about. And these two elements also have a very important role to play in the algorithm of molecular dynamic simulations. Today, we'll also cover a little part of initialization, but to be more, we'll have a better understanding about initialization in one of the next lectures. But in this class or in this particular lecture, we would have a very uh, simple way of understanding towards initialization aspect also. So let's start with cutoff radius. So the concept of cutoff radius can be implemented or can be explained in different setups. But since we are already familiar with LJ potential, I thought of keeping LJ potential on the foreground and then explain the concept of cutoff in relation to LJ potential. But to be very frank, this potential is very much the same, or this particular cutoff concept is very much the same for any potential that we consider in our system. So just to give you a briefing about what LJ potential is all about, and for a very quick review, I would say that the x-axis and the y-axis that we have on this curve or in this plot, where x-axis is the separation distance and y-axis is the potential that we have, and this curve is what we call as potential curve. And since this is a Lennard-Jones potential curve, which is meant for pair of particles, we have, if we have two particles separated by some distance, we can simply look at their separation distance on x-axis, and looking at the separation distance on x-axis, we can find out the potential corresponding to that distance on this curve. So the advantage of using this curve is this curve will tell us what is the amount of force that we experience between the particles if their separation distance is known. So like this is the potential and this is the separation distance of the particles. If we know the separation distance of the particles, we know the potential existing between the particles. And if we know the potential, we can simply take the negative gradient of potential to obtain the force. So force acting between two particles separated by distance r can be very easily known when we know this potential curve. So in other words, if we have this distance along the x-axis, at one point, we can simply find out the slope of this curve, and the slope itself will tell us the quantity of force acting between those two particles. And if you're wondering how this potential can be calculated, or what are the terms involved in this potential calculation other than the separation distance r, then I would quickly tell you that epsilon and sigma are the two properties of curves that we also have in the potential function. And if you could recall, epsilon is the energy, that is the y-axis is energy representative. So epsilon is the energy that we have for this curve at the bottom of the well. So if you measure the distance from x-axis to the very bottom of this well, this is called potential well. This distance is nothing but the epsilon value. And similarly, sigma is the distance from y-axis to the point where the potential curve is meeting on the x-axis. So this distance is sigma. So if we know the potential curve, these two values are already known to us. So epsilon value and sigma value are already known to us. So if we have a pair of particles, we can simply compare them on this plot with their separation distance and quickly find out the force existing between them. By looking at the very nature of this curve, you can say that it has two elements in it. So this is the reflective part or the repulsive part. And this part that you have from the bottom to the rightmost end is the attractive part. So the attractive part is not as steep as the reflective part. And if you observe, the attractive part or this particular right side portion would try to meet the x-axis at infinite distances, meaning that in all possible practical limits, the curve will never touch x-axis, and it is always trying to touch the x-axis, which kind of implies that the slope is constantly changing from this point as we move along with greater distances. And this should ring a bell in your mind. If if slope is constantly changing, we'll still have force, although the particles were separated by a very huge distance. And that distance will not be much because the slopes are very negligible or very much close to zero as we proceed towards the larger distances side. So no matter what distance you actually have the particles separated with, we still have some effect of attractive force acting between them. But the point that we have to note here is because this force or the slope is very little, the effect experienced by the particle because of this attractive force is very minimal. So it is quite wise option to ignore all the force calculations after a certain limit of distance. And that's the point where we introduce the concept of cutoff. So if we implement the cutoff scheme, we were trying to reduce our computational intensiveness by removing all the calculations which have the separation distance more than a certain value. And that limitation value that we put as a bound is what we call as cutoff radius or separation distance or cutoff separation. So R cut or cutoff radius is the place where we kind of truncate the force calculations. So any particles which were separated beyond this distance were not considered for force computation. By doing so, we were reducing our burden of calculating forces between all the particles. So I want you to focus on this part, and I want you to see and observe what exactly are we going to do in terms of implementing cutoff to this potential. So if we use the same curve, there still exists some slope beyond this point. So we have to slightly modify this curve so that the slope becomes zero or this particular curve gets transformed into a new one so that our cutoff can be implemented. So the very first way of doing cutoff is this. So this is called abrupt cutoff. So up until this point, we pretty much follow the same Lennard-Jones potential original curve. And in the close proximity of this cutoff radius, what we do is we suddenly jump from LJ potential to x-axis. So this is the place where we were changing the potential. So it is simply understood that we were calculating the forces up until this point, and if we cross this limit, we were just simply ignoring the force calculations at all. This is a very simplest way to do it, but I hope you have already noticed that there is a very clear cut disturbance or very clear kind of disturbance in this curve. So because of this sudden variation in the slope, we'll have the curve blowing up in the computations. So this is not really good. If we have a smooth curve, we can feed that smooth curve to the computations and then we can have a continuous solutions possible. But if some sort of curve similar to this abrupt cutoff curve is given as an input in your computer simulations, then this has to suffer because of its discontinuity observed in this R cut. So this discontinuity is not really good for small calculations or for basic level calculations. We can still go with it. But if we have a very complex system or if we have a very system in which we want to focus on the accuracy of the particles behavior, then this cutoff is not recommended at all. So let's look at another possible way of implementing the cutoff. The next possible way, yes, as you observe, this is the next possible way. This is called simply shifted potential. So you might have already observed that the curve that we have here the original curve, that has been shifted slightly above so that it would reach to the x-axis within a close proximity from the cutoff radius. So within a very short range from cutoff radius, it would try to meet the x-axis. And once it meets the x-axis, we would truncate it off. So there are no sudden changes in this curve. And this looks quite good because the continuity of this curve is not compromised anywhere. The curve is smooth. The original behavior of the curve is also there, but the possible source of error in this particular case, in this particular scheme, is with the well depth. We have compromised on this parameter. So if epsilon is the well depth, we were compromising on this particular parameter, because of which every force calculation that we make from this point, from throughout this range, were not going to be same to that of original potential. So we were compromising on pretty much all the force computations when we are actually using this shifted potential. So we have to have a better compromise between all these features, and this next model that I'm going to show you is the best compromise that we have found so far. So in the next model, we have the original potential curve up until this cutoff radius. And from this cutoff radius, we have created a high order polynomial curve, which would smoothly take the transition from the actual potential to the x-axis. Hello, could you hear me?
Now you're back. There was some
Okay,
gap.
okay. So this curve stitches the original potential curve and try to shift it from original potential to 0 on the x-axis with a smooth trend. So there is no loss of discontinuity. There is no loss in terms of discontinuity, or there is no compromise in the value of epsilon. So this is the best compromise that we have made on implementing the cutoff. And this method is called switching method or switching potential method. So this is just for information, but for most basic calculations, we can still go with it. But this suffers some kind of particle behavior when we are close in the close proximity of